H is CP1. This has a complex subvariety, but this is not true in general. Namely, sorry about that. So. Hamiltonian torus action given by the Gelfand-Cetlin systems is not homomorphic. So the inverse image of the face delta lambda is not necessarily complex subvariety. For example, in this picture, so the image of these lines are complex subvariety, but the image of, for example, this face is not complex subvariety. The torus action does not preserve the complex structure of this space. And moreover, not necessarily complex subvariety nor a cycle. So in this case, the inverse image of this triangle is not a cycle. So if we take the union of these two faces, then it is a cycle. And in fact, so and take its homology class, then this has a Schubert class. This is a Schubert class. So in a toric, right, in a flag manifold, so the homologies are generated by Schubert varieties. And in this case, for example, the two-dimensional Schubert variety is, this has a shape of Hilbert surface F1. And so this has 4 B, I think. So this has 4 P1s. And this P1 corresponds to this one, and this one, and this one, this one. And the inverse image and this Schubert variety intersects at these 4 P1s. But the interior is does not intersect.
So you had that Lagrangian sphere.
Yeah.
So that's not a cycle.
But that is 3 dimensions.
Right.
And in the flag manifolds, the 3-dimensional homology is trivial.
Right.
So that bounds something. I don't know. I don't know how to see that.
You use cycle is a homology cycle or inverse cycle?
Homology. Yeah.
Not homology.
And this is studied by Kogan that T equivariant Schubert This is just a variety, not variety, just a class. Given by inverse images of some union of faces. This is described by the combinatorially described. And let me give one more remark. So we are considered a full flag case, but we can consider the partial flag case also. So for simplicity, we consider the case of Grassmannians and Grassmannian. Then this corresponds to the co-adjoint orbit with lambda satisfying this condition. Lambda m. Then on the orbit of this lambda, we can also consider the set of functions. We have the functions like this. But from this condition, this part has to be constant. And again, this part has to be constant. So only these functions are non-constant. If we think of this as a part of a square, then this has a shape of parabolic subgroup. Such that it's the Grassmannian is just identified with. This is the same shape as the matrices in this parabolic subgroups. So that means, the number of the function in this part is the same as the dimension of Grassmannian. Then we have a completely integrable system on the Grassmannian.
So what's the picture meaning? Please send the picture.
I'm sorry, I forgot to write the definition of the Gelfand-Cetlin system, a point of. I'm sorry. So Gelfand-Cetlin system, Gelfand-Cetlin Politop, So now we fix the data lambda 1 to lambda n. Then we consider the lambda ki, the functions. Then the image of the moment, image of the Gelfand-Cetlin system satisfies this condition. When we consider the size of n minus 1, then these eigenvalues satisfies these inequalities. So the first eigenvalue has to be contained in between lambda 1 and lambda 2 and so on. This is just a simple algebra, linear algebra. Then repeating this process, 2, 1. I'm sorry. So the image of the Gelfand-Cetlin system has to be satisfied these inequalities. This gives a polytope in a large n. And this is the Gelfand-Cetlin polytope. I'm sorry to say that, or forget to say that.
So in the F3 case,
yes, and in this case, this is just a lambda 2, and lambda 1, 1. This satisfies this condition. Then draw the picture for this. We get this one. And then this point corresponds to lambda 2, lambda 3, lambda 1, and lambda 1, 1. Then these two are equalities. Then this has to be the same. This corresponds to the point. Each equality corresponds to a face, codimensional face. So here 4 faces are intersecting at this vertex. This corresponds to these 4 equalities. Then go back to this Grassmannian case. We can consider the same thing. Then here we assume that lambda 1 to lambda r to be the same, and also assume to be the same. Then this point has to be constant, this part, and also these points, these functions are constant. Then we have the non-constant functions appears at this square. The number of this function, the function in this part, is the same as the dimension of Grassmannian. That's why we have a completely integral system for Grassmannian.
So the polytope is all possible.
Yes, all possible. Yes. Yeah, right. Yes. The sopro is fixed, and these are the coordinates on this. So this is the remarks for Gelfand-Cetlin systems. Next we go to the part on the toric degeneration of the flag manifold. So first recall that we recall some basic properties for toric varieties. Projective toric variety, projective toric variety is embedded into a projective space by using monomials. Ci alpha. Alpha is the integral point of the momentum polytope. And equivalently, the defining equation for the toric variety is given by binomial relations. So that means if alpha and beta, if alpha I and beta I is a points of several points in the momentum polytope, then it satisfies this condition. Then monomial satisfy this deviation. This binomial relation. So the monomials are generator of the graded coordinate ring, and these binomials are the generator of the defining ideals for the toric variety. So this is a case of toric variety, and in the flat case, flag manifold is embedded by Brückner coordinate Pi, and equivalently defining equation is given by Brückner relations. So Toric degeneration of F is given by deforming Brückner coordinate into monomials, or deform the Brückner relations into some binomials. This is what we want to do. And we will take this point. And the following construction is to Kogan and Miller. The construction is useful for the deformation of Gelfand-Cetlin systems. So introduce weights for the coordinate of GL and C given by upper diagonal part is trivial. And 1 here, 3 here, and 3 to the n minus 2. And T is a parameter of the deformation. we take the subset in the set of n to the 1, and this space set, and define the function q z t to b. So we first consider this matrix. So each component, each entry has weight, have a weight this defined in this matrix. Then take its submatrix and take its determinant. And divide some monomial in T. This is just given by Wij J. So this part is just a way of the diagonal term in PIZ. This means this is just a Z to the ZI11, ZI2 to ZIK. Then the point here is that this diagonal term has the smallest weight, namely, so diagonal term is unique term of lowest weight. So this is a polynomial, of course Zij, and also in T. And this is the unique term. So Qi Gij and 0. We actually put T to be 0. And this is a diagonal term of Pi. And this is monomial. Using this, we can construct a deformation of Lag manifold into a toric variety. So X or X n to be is a subvariety of projective space, product of projective space times C. Given by the relations for family of projective varieties, given by relations for these functions. If t is not equal to 0, and also
So where does this weight come from? This
three. The the 3 is not so important, but it is important that this number has to be bigger than 2. When this is 2, then this is, so this uniqueness doesn't hold. And equip scalar form on X so that どうしましょうかね。Restriction to each fiber coincides with this form. On the flag manifold, this coincides with the constant Kirillov form. Then theorem by maybe some other people that this map is denoted by F is a flat family of projective varieties or scalar varieties. Such that the fiber over 1, so if t is equal to 1, this is just a Pripka coordinate. So the fiber over 1 is just a flag manifold. And the central fiber, this is a toric variety, since this is monomial. And actually, this coincides with the Gelfand-Cetlin variety, toric variety, which corresponds to the Gelfand-Cetlin polytope. And general fiber, if it is not equal to 1 and 0, then its fiber is isomorphic to a flag manifold as a complex manifold. But if we consider this symplectic form or scalar form, then this isomorphism is just as a scalar manifold. In this case, this on the restriction of this symplectic scalar form is a torus invariant scalar form. We see the example of three-dimensional case. The three-dimensional flag manifold is embedded into the product of two projective spaces, C3. And this is just two copies of P2. And this is, so when we write the homogeneous coordinate of these spaces like this, Z12, Z13, Z23. Then this is three-dimensional, and this is dimension 4, and this is a hypersurface in this space. And its defining equation is given by Z1, Z23 minus Z2, Z13 plus Z3, Z12 is equal to 0. So this is the physical embedding of the three-dimensional flag manifold. And in this case, the family is given by this equation. T appears here. So when T is equal to 1, this coincides with this empirical relation. And if T is equal to 0, this is given by this binomial relation. And this is singular act. Z1 is Z2 is Z23, Z13 is equal to 0. And this corresponds to the vertex. I'm sorry. Oh, this vertex. I don't give the proof here, but so why this central fiber corresponds to the Gelfand-Cetlin polytope. But when we see that the Gelfand-Cetlin system is also deformed into the moment map on the Gelfand-Cetlin variety, toric variety, then we see that the central fiber actually corresponds to the Gelfand-Cetlin toric polytope.
So XL is the dimension of the divisor.
I'm sorry?
XL is also divisor, right? P to cross P.
FL.
XL
Yeah.
dimension of the divisor.
Divisor. Oh.
That is a divisor in P to cross P, right?
In this case, yes.
XL is also divisor.
Yeah, S3. But in general, this is not true. Actually, general flag manifold is not completely a complete intersection in product of projective space. Maybe this three-dimensional flag case and Rassmann of T4 is only the hypersurface case.
T is equal infinite case or what's the T equal infinite?
T is infinity. Infinity is just a intersection, just a union of two planes. Just this part remains.
So when you say Gelfand-Cetlin toric variety,
Yes.
it is a toric variety.
Yeah, toric variety. This is constructed from this polytope.
But that polytope does not give, I mean, this Gelfand-Cetlin polytope does not give you toric variety.
Yeah, actually, it defines the toric variety, singular toric variety.
It defines singular.
Yeah, singular toric variety. And this is the toric degeneration, but this is not so nice for our purpose because to define the Gelfand-Cetlin system, we used the smaller unitary group actions. But this has, on the space, there is no such group actions. So we can.
Polytopes stay and polytopes from toric variety and polytopes from plane manifold are same.
I'm sorry, I don't have
We have two polytopes. Right?
polytope. We start from the Gelfand-Cetlin polytope. Gelfand-Cetlin polytope are given by fixing the data lambda. But actually, this, but the toric variety does not depends on the choice of lambda. So anyway, we start with the fixing the data lambda. Then we can construct a Gelfand-Cetlin Gelfand-Cetlin polytope. Define so like inequalities of triangular shape. Then using this polytope, we can construct a toric variety. And this is the Gelfand-Cetlin toric variety.
The question is where we start with GL and NR and we divide by polytope, right? You were talking about the polytope? No? Sorry.
Yes.
So from the flat variety to the polytope is 1-to-1. So you mean the two different flat variety can keep the same delta lambda?
So we consider the flag manifold as a symplectic manifold. Fix a symplectic structure, then so the polytope and the flag are one-to-one correspondence. Actually. So this corresponds to fixing, considering the adjoint orbit. This is one-to-one correspondence, and also the choice of lambda defines a Gelfand-Cetlin polytope uniquely. And what we actually need is degeneration in stages.
Deformation, which deformation?
Which deformation?
So, zero is toric, right?
Yeah.
So you think about toric, deformation of toric, right?
No. General fiber is a flag manifold. This is not a toric variety. So this is deformation as a projective variety. In the central fiber, only the central fiber is a toric variety.
So you may consider that as a smoothing of
This is smoothing of this singular toric variety.
And that depends on the Kähler form, right?
No. If we forget the Kähler form, then this is just a flat deformation of the projective variety. So, if we forget this symplectic form of a Kähler form, then this is as a complex manifold. This equality is just as a complex manifold.
Does this has kind of universality? This flat family. So we have just one flat family.
Yeah, this is just one flat family. Maybe there are many. I'm not sure, but there are other construction of other family will be. I'm not sure. And what we need is this degeneration in stages. This respect smaller unitary group actions. For that purpose, we introduce multi-parameters. So from T2 to Tn, n-1 parameters. And consider the following weight little bit complicated. I don't want to write. T3 square T4 to the 6. Tn something in the minus 3 T1 T3 T3 T4 to the square and something 1 Tn and something. A little bit complicated. And using this weight, will be weight of diagonal inverse times Pi of this matrix. So this is a little bit complicated, but point is very simple. I mean, so the first we choose this weight so that when we assume that all parameters are the same in the diagonal, then this coincides with the previous one parameter family. And the second one is, this is again the polynomial in t variables. And maybe the most important one is the parameter tk appears in the kth row and below, does not appear above the kth row. So these three are only the requirement for this weight. Then using this Q tilde, we can extend the family to n-1 parameter family of projective varieties. Maybe we should tilde.
But it seems to me it's
Yes.
K from K plus 1 to row and
Yes.
below, maybe
Keep, for example, T2 appears in the second row.
I'm sorry, I see.
So the previous matrix started with zero diagonals.
So in the previous one, this is just consider T to Ij. This is just a T2 to 0. Sorry. So I think this is a little bit confusing, but the same. Then from this property that the fiber over 1111 is now flag manifold. The fiber over 0000 is this toric variety. And the point here is that So if we define x sub k to be the restriction of x tilde to T1, I'm sorry, T2 to Tk minus 1 is equal to 1, and Tk plus 1, Tn is equal to 0. So this corresponds to the family of with parameter Tk. And we denote, I'm sorry, so we write the fiber over T by x sub kt. Then from this property that xk has an action of uk minus 1. Since we assume that the kt2 to tk minus 1 is assumed to be 1, then we have an action of u to u of k minus 1. And moreover, there exists a torus action. So here we call that I'm sorry? Yes, fiberized. So this is the coordinate for the Gelfand-Cetlin polytopes, and each of lambda ij gives a torus action on the Gelfand-Cetlin toric variety, the Hamiltonian action of this function. Then, we divide this torus action in the rows. Then there are n-1 functions. Then this gives a n-1 dimensional torus acting on this x0, and also this row corresponds to a two torus action, and also this acts on the x0. This one. So we divide the torus action on this space in this way. Then this space has action of subtorus of t minus 1 tk 5 hours. And then we use to consider the piecewise linear path. Starting from 1, 1, 1, they first move the last parameter to 0. And then we vary the next one, and so on. And finally, we reach to the origin. This is what we will consider. This sequence is important for the construction of toric degeneration of Gelfand-Cetlin systems. But here is a remark. So now we have n-1 parameter. So this consists of n-1 stages. But the final stage corresponding to this first parameter. This is a trivial family. This is because I will explain this part later, but so this part corresponds to the deformation of flag manifold for n equal 2, and this is just a P1. This is already toric variety, and this does not deform. This is the reason, but so we will come back to this point later. So for example, in the case of n equal 3, then this is essentially only one stage, consists of one stages. Just I erased to here, but this is just one usual. Wait. And using this degeneration, we construct a deformation of Gelfand-Cetlin systems. Well, first, I'd like to write the statement of the main theorem. So for each stage, there exists a set of functions such that the restriction of these functions on each fiber is a completely integrable system. And xk is the end of this stage, and this coincides with the start of the next stage. On this space, so we just simply write this by phi kt. Then on this space, the restriction coincide. So this means this is continuous on this piecewise linear path. And this is the starting point of the piecewise linear path. Then the manifold is a flag manifold. On this space, this is a Gelfand-Cetlin system. And on the end of this degeneration, this is the Gelfand-Cetlin toric variety. Then on this space, this is the moment map of the torus action. So phi tilde gives a family of completely integrable system connecting the Gelfand-Cetlin system and the moment map on the toric variety. This is the first part of the statement.
It is actually integrable system, right? It is actually integrable.
Integrable.
Right. Sorry.
Sorry.
Never mind. Is the right proposition? So it is actually integrable system. Right? No? So the system is actually so the bracket is 0, right?
Yes, yes.
Right.
So right.
Right. And the second part is that there exists a flow on the space. So denoted by phi kt. This sends a fiber of this family to another fiber. Preserving the structure of completely integrable system. So a priori, this is just a map into Rn, but in the beginning, at the starting point, its image is a Gelfand-Cetlin polytope, and this means that the image does not change under the deformation. So this is always the Gelfand-Cetlin toric variety. So in particular, we see the endpoint of the degeneration. We see that this toric variety corresponds to this polytope. And construction is very explicit. So now we have the action of k minus uk minus 1 and torus. So we can consider the fiber-wise moment map. I'm sorry, maybe just consider the moment map. K minus, I'm sorry, n is moment map, and take its eigenvalue, we get a function. This is just an extension of the Gelfand-Cetlin system of um action, action for m is less than or equal to k minus 1. And also we can construct a moment map for this torus action. Momento map of Tm action. Here m is greater than or equal to k. Then phi tilde is just given by these functions, namely k. This corresponds to this torus action, and the smaller part comes from the unitary group action. And from the construction, we can rather easy to see that these properties. I'm sorry, so for example, we see this. The flow is also very explicitly constructed. This is, we use gradient Hamiltonian flow defined through this by Weizhong-Luan. We think of Fk as a holomorphic function. Part. This is Hamiltonian vector field. This is nothing but a Cauchy-Riemann equation. Then we divide by the square of norm. And we set this vector field to be Vk. Then phi k is given by the flow of this vector field. So then if we differentiate the real part of Fk by this vector field, then from this expression, this is always minus 1. I'm sorry? Fk is a family, a map of the family. Fk? Fk is, this is just a family, this is Fk. This is, so Fk is a family of the, we consider this as a holomorphic function here. And take its gradient or Hamiltonian vector field. Then we differentiate the imaginary part. Then we use this expression. Then this is the Hamiltonian vector field, so this is 0. So this map xk1 to xk1 minus k. And this, so we divide the Hamiltonian vector field by this norm. So this is not the Hamiltonian vector field, but we can show that this map is preserve the symplectic structure on each fiber. So this gives a map as a symplectic manifold. This is the definition of this flow. And I'll finish my talk with the idea of the proof of this theorem. So now we see the end point of the first stage. Then we have something x n 0. This is the starting point of next stage. And there is a resolution. That's that. This has a structure of vibration over smaller flag manifolds with fiber P1, the product of P1. Then now we have the action of un minus 1 and tn minus 1. Then we pull back the action on this total space. Then this action comes from induced by the standard action on this flag manifold. And the action of torus, it comes from the action on the fibers. So if we pull back everything on this resolution, then we can see very explicitly that the functions are Poisson commuting or coincide with the next stage or something. We can see this. So, I have to say moreover. So we have an n-1 family, parameter family, and then we restrict the last parameter to be 0. Then we can construct this on this. We can lift the construction on this family. So there exists a family, which is a fibration on the family of deformation of n-1 flags. Then we can use this structure to see these functions are Poisson commuting and so. And the final comment here. So then we go to the end of the next stage. Then we can again blow up to construct a fibration structure. And so then we continue the process. Then we have a resolution of x0. This is small resolution, such that this has a structure of P1 to the n-1. Structure of iterated fibration over P1. This is the same as a small resolution constructed in your paper. And the existence of small resolution is very important for the discounting problem. I'll stop here.